On July 25, 2026, Ramana Kumar published a repository containing a supposed breakthrough in mathematics. This formal document displays what appears to be a machine-checked disproof of the Collatz conjecture. Crucially, it contains 0 sorry commands, the placeholders used when a proof is incomplete. According to the system's validation indicator, the proof is mathematically flawless. Kumar produced this repository with the assistance of an AI model. The mathematics inside the proof were completely invalid, yet the official lean kernel accepted the logic as absolute truth. In formal verification, kernel soundness is the bedrock of the system. The kernel is the final arbiter of truth. If it accepts a false proof, the entire foundation of mathematical certainty collapses. This was a reproducible bypass of the system's core logic. The exploit successfully forced the kernel to validate an objective falsehood. An AI-generated proof of false infiltrated a production verification kernel. This event forces a rigorous reevaluation of the automated theorem-proving infrastructure we rely on. This flowchart illustrates the architectural divide within the lean verification system. User input first enters an Elaborator, which processes and passes structured data down to a completely isolated kernel. The front-end Elaborator handles standard type checking. It translates human-readable code into formal expressions and catches obvious errors before they can proceed. The invalid Collatz script contained blatant mathematical errors. It could not have survived standard front-end validation. To bypass the Elaborator, the exploit utilized metaprogramming, writing code that generates or manipulates other code. Metaprogramming allows a user to send an inductive declaration directly to the isolated kernel block. This completely bypasses the front-end checks. Sending declarations directly to the kernel is an intended feature of the system architecture. The Elaborator is designed for user convenience, not absolute security. Because the front end was bypassed entirely, this exploit exposes a failure in how the kernel processes raw, unvalidated mathematical arguments on its own. The exact vulnerability resided in the kernel's handling of nested inductive types. This abstract syntax tree represents a nested inductive type. When the kernel encounters nested occurrences, it must generate a new auxiliary type to eliminate them, mapping parent nodes to subsequent parameter nodes branching beneath it. A phantom parameter occurs when a parameter is passed to a type, but is never mentioned in constructor fields. During processing, the kernel failed to include them in the auxiliary type. These dropped parameters completely escape type checking. The exploit weaponized this exact omission. An intentionally ill-typed argument was placed squarely in the phantom position. Because the auxiliary transformation deleted the ill-typed argument before verification, the kernel evaluated an incomplete structure and was tricked into accepting a smuggled proof of false. This bug was a C++ implementation flaw in the software logic. It was not a hole in Lean's underlying mathematical metatheory. A single missing variable check in the source code compromised the absolute certainty of the entire verification system. Following the exploit, developers looked to nanoda, an independent Lean kernel written entirely in Rust by Chris Bailey. Independent checkers verify proofs against a completely different codebase. They act as a failsafe against software implementation bugs in the primary system. The fake Collatz Disproof successfully passed a recent version of nanoda as well. Nanoda did not share the phantom parameter bug. The Rust implementation correctly checked that specific syntax node. This split-screen comparison shows the data traversing both logic trees. Nanodea failed due to an entirely separate software bug, a missing type name verification in a projection node. The AI-assisted proof was constructed so precisely that the specific expression ignored by the official Lean kernel was the exact same expression accepted by Nanodea's projection node bug. Ramana Kumar suggested this overlap was coincidental timing. Joachim Breitner, who reviewed the fix, proposed a different hypothesis. Breitner hypothesized that modern AI models possess the capability to identify and thread the needle between overlapping zero-day vulnerabilities across independent systems simultaneously. If AI models can systematically map and exploit simultaneous blind spots in independent tools, the standard defense of verifying proofs across multiple systems is no longer sufficient. On July 28th, Karen Gopinathan reduced the massive Collatz exploit down to a minimal proof of false, cleanly isolating the bug. The Lean development team pushed and merged a patch, fixing the phantom parameter bug within 1 hour of Gopinathan's report. To prevent this specific attack vector from returning, new regression tests were immediately introduced into the kernel arena. The response escalated with the involvement of OpenAI's Daniel Celsum. Celsum deployed a specialized cybersecurity AI to conduct a massive, comprehensive sweep of the entire Lean kernel codebase. This automated sweep discovered multiple other implementation mistakes hiding inside the Lean kernel. Like the Collatz exploit, all of these newly discovered bugs were only reachable via the metaprogramming bypass. Every newly discovered vulnerability was patched, and the kernel invariants were hardened against future direct attacks. The immediate threat was neutralized in record time, but securing the system required deploying AI auditing tools to fight an AI-assisted exploit. In the discussions following the exploit, a common community suggestion emerged: restrict or remove metaprogramming to block the attack path entirely. Restricting the front end is a flawed approach to security. The Elaborator is untrusted by design. System soundness cannot rely on an untrusted component refusing to build a bad term. This schematic shows alternative attack vectors that exist even without metaprogramming. A bad actor can write .boolean compiled files directly, bypassing the Elaborator block entirely to strike the isolated kernel block. An attacker can also modify system memory directly. This proves the kernel must act as an independent, sealed vault. The core philosophy of proof terms dictates that the kernel must be capable of rejecting ill-typed declarations on its own, within its own isolated process. True architectural security relies on strict separation of concerns. The kernel must assume all external input is malicious, regardless of how it was generated. Checking proofs with independent kernels still functions as a defense, provided users constantly update both systems to eliminate overlapping stale bugs. The ultimate theoretical defense lies in projects like Mario Carnero's Lean for Lean. Lean for Lean is actively working to mathematically prove that the Lean kernel perfectly implements Lean's type theory. Once complete, this will eradicate implementation bugs entirely. That long-term mathematical defense contrasts sharply with the immediate reality. AI models are currently probing kernel boundaries vastly faster than human engineers can review them. As we increasingly rely on machines to write complex proofs and use machines to find the flaws in those exact systems, the definition of a machine-checked truth requires constant, vigilant defense.